Hey, stats. We are done with sections that we're going to do out of the book. So for these last couple days, I want to kind of go through some really important stuff that we've done throughout the year. So we're going to start by, actually, let me just show you what I have planned out for these next 5 days. So you guys are done on Friday. So you only have 5 days left. That's it. Nothing next week. They said seniors are done May 1st. So that's kind of exciting. So today we're going to go through, today and tomorrow, we're going to go through probability. So we're going to fill this chart out. This I've attached to Google Classroom. And this is a good sheet to keep in case you end up taking college stats, because that probability section of college stats is going to be really easy when you have the formulas and stuff for this all ready to go. So we're going to do probability. These 2 days we'll fill out this grid. So we'll do half of it today, half of it tomorrow. And then Wednesday, Thursday, we're going to do chapter 1 vocab. There's some sections in there that talk about, categorical data versus quantitative data and kind of going through that stuff again. So we'll do that Thursday, Friday, and then, Wednesday, Thursday, and then Friday, we'll talk just a little bit about z-scores one last time before we are done. So print this off if you haven't already, or contact me and I can print it for you. But this is the probability grid that we're going to fill out for this section. Okay, so we'll fill half of this stuff out. I do have a section that I want you to add to the bottom here, and we'll get to that. So for this video, we're going to go over these first 3 on the top, and then I have 3 sections that I want to add to the bottom here, which talk about permutations, because there's more than one type of permutation. So starting with the fundamental counting principle, I'm going to start with an example that would use the fundamental counting principle. So this would be like I have 3 pairs of pants, 4 pairs of socks, 5 shirts, whatever. How many outfits can I make? It can also be like, let's say I have 3 poster boards. Let's do this, 3 poster boards, 4 markers, and 2 colors of glitter. How many combinations can I make out of that? Okay, so the equation for this, for fundamental counting principle, is just going to be n1 times n2 times n3 ... And you would continue to do that. So n is going to be each one of the, I'll say number of choices each category. Okay, the number of choices for each category. So for a solution for this example, we would say 3 times 4 times 2. 3 times 4 is 12 times 2. That's going to give me 24 total different poster boards that I could make. Okay, so fundamental counting principle is just the most basic one. This is based off of a tree diagram. So if I would make a tree diagram out of this fundamental counting principle, I would start with the 3 different poster boards that I could have. So 1, 2, 3. Then from each one of those, I could choose 4 different markers. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4 out of each one of those 3. But then each one of these will have 2 branches off of those. I'm going to run out of room. You don't necessarily have to draw this in here. Okay, so looking at my my longest, or I guess my lowest row, there are 24 of each one of these. Okay, options going all the way through here. So I could maybe choose a red poster board with a purple marker and gold glitter, or maybe red poster board, purple marker, and silver glitter. Okay, would be another option. And going all the way through there are 24 different combinations that I could end up with on the very lowest level. Okay. All right, so permutations. The most basic permutation is choosing. Let's do this. Starting off with the example, I have 5 students, and I want to choose a president, vice president, secretary. Choose president, vice president, secretary. Okay, how many ways? How many ways? Okay, so this is another counting problem. Like, how many ways can I choose a president, vice president, secretary out of 5 students? Okay, so the equation for this, or the way that we set this up, is NPR, where N is the total number and R is the number that we're choosing. Okay, so in this case, we have 5 total students and we're choosing president, vice president, secretary. And that is going to be choosing 3, so I would have 5P3, okay? And then we can figure out what that is by typing it into our calculator. I'm also going to write the formula out here for you in case you ever would need that. It is n factorial over n minus r factorial, okay? So that's what the formula is. We're just going to plug this into the calculator because the calculator is going to do this for us. But one other important piece of information is that order matters in this case. Order matters, okay? So when I'm doing president, vice president, secretary, the order matters because if I would choose, you know, Michaela, then Katrina, then Jace, in that order, that would be a whole different combination than choosing Jace, Katrina, Michaela, or you know, whatever, because each one of them has a different role. So the order in which I choose them, president, vice president, secretary, does make a difference. Okay, that's why it is a permutation. Okay, so I always think of permutation and president. President and permutation both start with P. Order matters. That's how I know to do permutation. So on a calculator, grab that thing. If you have a calculator that looks like this, I think we've done this before, so you should know where these buttons are. Type in 5 first. This one has a PRB button. You might have to search for yours. If you cannot find this, either ask me or Google it. I always Google everything. So 5P3 is what this will look like, and then I'm going to hit enter. So there are 60 different ways. 60 different ways of choosing a president, vice president, and secretary. Okay. All right, then if I go to combination, combination is one where order doesn't matter. Order does not matter. Okay. Still have NCR, and we have N equals the total, R equals the number that we're choosing. Okay. And so the example that I use for this, I'll still use 5 and 3. So 5 students, students, 5 students, 3 for, what committee do I want them to be on? T-shirt committee. We're going to be designing t-shirts. I don't know if I spelled committee right. Anyway, 3 students to be on the t-shirt committee. Okay, now the order in which I choose them does not matter. It doesn't matter which name I draw out of the hat first because they're all going to be doing the same job when they're a part of a committee. So C for committee, C for combination. That's how I know that I'm going to be doing this guy. And so the formula for this is n factorial over n minus r factorial, the same as permutation, except because the order doesn't matter, I'm going to divide out all of the repeating ones. So basically in this case, choosing Jace, Michaela, Katrina would be the same as choosing Katrina, Michaela, Jace. So I have to divide out those combinations where they're in a different order, but they're using the same 3 people. So in that case, this is going to be 5C3, and I would have, let's go back, 5C3. I would have only 10 combinations in that case because we're dividing out the number of repeats that we have. So it will always be true that when you have permutations and combinations using the same numbers, combinations will be fewer than permutations because here order matters, so each individual way that you're ranking them has a place, whereas here it doesn't matter which way you're ranking them, so you're dividing those out. Okay, so those 3 are kind of some important ones or some important formulas to have or to know. I'm going to go down here, and these are all permutations. So we're going to fill these bottom 3 out, and I'll kind of show you how these work. So these are special permutations. So the first one is choosing all n of n. Okay, so this would be kind of like a permutation where I have npn. Okay, it's really npr, but you're choosing all three, or all you're choosing all of the students. Okay, so example of this would be like, let's say I have I'm assign numbers 1 through 5 to 5 players. So I have jersey numbers 1 through 5, and I am assigning them to 5 different players. Oh, shoot. My pager's going to go off. Hold on. All right, so in this case, I have all 5 players that are going to be involved. I'm not choosing like 3 out of 5 of them. Everyone is going to get a jersey number, okay? So in this case, for the solution, I have these 5 players. I always list a little, thing here. And that first player, whatever player gets to choose, they have 5 jersey numbers to choose from. Okay. The second player, after this one has chosen jersey number 4, this one only has 4 numbers to choose from. Okay. Let's say they choose the number 1. Okay. This person only has 3 numbers to choose from because 4 and 1 have been already taken. So they're going to choose the number 2. Let's say this person only has 2 to choose from. They can choose either 3 or 5. Let's say they're going to choose number 5, and this person's stuck with only 1 jersey number, which is number 3. And so the number of ways that I can, kind of like assign them jersey numbers would be 5 times 4 times 3 times 2 times 1. So another way of writing that is 5 factorial. Okay, 5 factorial I can do in my calculator. So I have 5. I go to that same spot as I did before. I go to the PRB button. Let me go down. PRB button has that factorial. Okay, so I have 5 factorial, enter, and there's 120 different ways that I can do that. Okay, so I could have also, instead of doing 5 factorial, I could have done 5p5 because I'm choosing all 5 players, and it would give me 120 as well. Okay, so that's another way of doing that. Okay, so I'll put or n factorial, where n equals the number of items / people. Okay, I'm going to do one more example of this off to the side over here where we have, let's say, 4-digit code. Okay, 2, 3, 4. This one has to be a number. This one has to be 0 or 1. This one is a letter, and this one is a number. Okay, so in this case, this is another kind of permutation, but we have a number. This one can be a number. So there are 10 numbers, 0 to 9, 0 included. So 10 numbers here that this could be, right? Multiplied by this has to be a 0 or a 1, so there's only 2 things that could go in this spot. Okay, a letter, there are 26 letters, so 26 different characters could go in that spot, and then another number is another 10 here. Okay, so when I multiply those all together, let's see, 2 times 26 is 52, times 10 times 10, which is 100, so I have 100 times 52, or 5200. I can do that in my head. There's 5,200 total combinations that I can do for that 4-digit code if that's the way that it has to be. Okay, so there's another example of kind of permutation. Okay, now 2 other things if I have repetition going on. So let's say that I have, whose name did we choose before? We could use Cassidy. How about that? Okay, so example, Kassidy, Cassidy, okay? Cassidy's name has 2 S's in it, okay? So if I were to randomly put the letters of her name into a hat and draw them out, what I could do is I could choose this one first, this one second, third, fourth, fifth, sixth, seventh. I could choose the letters in that order, or I could choose 1, 2, this one third, this S third, this one fourth, this one fifth, sixth, seventh. And if I choose them in that order, it's still going to spell the same word, because this S, if I just flip those two around, will still spell the word Cassidy. Okay, so when I do that, I have to divide out that repeat. And so if I'm trying to figure out how many ways or how many words can be spelled with the letters of Cassidy's name, now really they won't be words, they will be non-words because they won't even make any sense. But how many different ways can I arrange her name, or the letters of her name? I would have to divide out the repeats because there's 2 S's in there. So the formula for this is going to be n factorial divided by, and I'll say r1 factorial times r2 factorial times r dot 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 dot. Okay, so if she had multiple digits that, or multiple letters that were repeating, okay, I would multiply by that by the bottom here. Okay, so in this case, Cassidy has 7 letters, so we would do 7 factorial divided by, she has 1 letter that repeats, but it repeats twice. So we would divide that by 2 factorial, okay? And we will get an answer. 7 factorial divided by 2 factorial, and we get 2520. So there are 2,520 ways of arranging the letters of Cassidy's name. Now, none of them will really make sense, except the word Cassidy itself, but there are 2,520 ways to arrange the letters of her name. Okay, so I'm going to do n equals total number. Let's do total number, and r is the number of repeats. Okay, so if we were to have another letter that repeated, we would be multiplying by, something else over here, like r2 factorial. Don't put that in there, but there's another letter that repeated, we would have to multiply by that. Okay. All right, last one is a circular permutation. Okay, so if they are standing, if I have people standing in a circle, I'm going to say 4 people at, let's say, a circle table. How many ways can I arrange them? How many ways? Okay, so to kind of illustrate this, let's say I have, who haven't I picked on? Let's do Layla here. We'll do Michaela, Macy, and Jace. We'll do those guys. Okay. So Layla, Michaela, Macy, Macy, Jace. If I have them in this order, I could swap like Layla and Michaela around, okay, to be sitting in a different spot. Or, I could swap any of these 2 people around and have another combination. But if I take every single person and I move them 1 unit to the right, okay, that is not going to be a different combination. Okay, if now Layla is over here, Jace is down here, Michaela and Macy, that is going to be the same combination because you are in the same spot relative to who you were next to before. So we need to divide those guys out as well. So this one is, let's see, n factorial divided by n, or you can do n minus 1 factorial. So a lot of people like to just do n minus 1 factorial in this case. Okay, so n is, I'll put the number of items / people. Okay, so 4 people at a circle table, how many ways can they be arranged? I would take 4 minus 1 factorial, which is just 3 factorial. Now 3 factorial I could do in my head probably faster than the calculator. 3 times 2 times 1 is going to be 6. So there's only 6 ways that I can arrange these people sitting here and have it work. Okay, otherwise just rotating them is not going to count. All right, so we'll fill in the last 4 categories in the next video, and moving on.